So right, we are starting our next chapter, thermal stresses. Okay, so actually this chapter is just a continuation of uniaxial loading only, not uniaxial loading, axial loading, whatever we discussed. It is just a continuation, but until axial loading, whatever we discussed, until the last concept what we discussed, until that we didn't said anything about change in temperature, right? If temperature changes or temperature doesn't change, we are not at all concerned about it. So we just left it off. We didn't say anything about temperature. But in general, what will happen? If I take any material and if I increase the temperature, okay, if temperature is increased, the material is going to expand. And if the temperature is decreased, okay, the material is going to contract. Listen carefully, this is a generalized statement. Okay, why I am saying it is generalized statement? Because there are some exceptions to this. There are some materials which doesn't follow this. Okay, that is due to the carbon atoms or it is due to the molecular arrangement of that particular material. Okay, but in general, if you take a solid material, okay, it's going to expand when the temperature is increased, it's going to decrease when the temperature is it's going to contract when the temperature is decreased. Suppose, let me consider something like this. I'm considering a material, okay, I'm keeping it in the oven, okay, I'm keeping it in the oven or I'm just keeping it somewhere, I'm increasing the temperature from 30 degree to 40 degree. If the temperature increases, what will happen to this? As I said, we are going to concern only about this case, we are not going to concern about the special cases. There are special cases where if temperature increases, material is going to contract, and temperature decreases, material is going to expand. Those are not the cases which we are going to discuss here. Here we are concentrating on this type of materials where 95% of the materials are behaving like this only. Okay, listen. So if I am taking a material, initially it is at 20 degrees Celsius, I am heating it, it is reaching 30 degrees Celsius. When it reaches 30 degrees Celsius, it's going to get expanded, right? It is getting expanded in the sense length, this height or width, and also this breadth, everything is going to increase. Similarly, it is at 30 degrees Celsius, like for example, you consider 20 degrees Celsius, I am decreasing the temperature to 15 degrees Celsius, it's going to contract, length, breadth and all, okay. And now if you see, if there is, okay, so I will expand this, if there is no restrictions, just keeping it on the floor and I am heating it, okay, I am increasing the temperature, freely it will expand, freely it will get contracted, okay, it can expand freely, it can get contracted freely, okay. So there will be deformation, but there won't be any stresses. Why? Because it is restricted. If there was a because it is not restricted, it is freely expanding or freely contracting. If it is restricted, for example, I am holding it in both the sides, I am holding it tightly in both sides and I am heating it, it will try to expand, but I am holding it. So due to this, it cannot expand freely. So what will happen? So it cannot expand freely, there is going to be stress which is developed inside. Why the stress is developing? Since I am holding it, right? Since I am holding it, I am going to offer a reaction force on this. Okay, I am going to offer a reaction force on this, and due to that reaction force, there will be compressive reaction force on this, so there will be compressive stress. Okay, so there are different cases we will see. Okay, so if I am heating if I am increasing the temperature, it will try to expand, and I am holding it tightly. That is, I am fixed. Okay, I am fixing it tightly, and due to fixing it tightly, my hand is going to offer a compressive reaction force, which is nothing but there is going to be compressive stress developed. Think about the converse case. If I am cooling it, what will happen? It will try to contract, right? It will try to contract. Again, I am holding it tightly. I am not allowing it to contract freely. Okay, I am not allowing it to contract freely. So what will happen? My hand, that is this fixed support, is going to offer a resistance, or it's going to offer a reaction force which is going to be tensile in nature. That is, it will try to expand it. Okay, so that is the concept. Okay, listen. So what is the conclusion which we got from this? If the material is free to expand, free expansion or free contraction. If temperature increases, or I can say that if there was any temperature changes, okay, I will just write it as temperature changes, because temperature increases means expansion, temperature decreases means contraction, right? So I will just write it as delta T. There was a temperature change, then no thermal stress is induced. And if there was a restriction, then, okay, if there was a restriction, with restriction, thermal stresses are developed, okay, thermal stresses are developed in that direction. What is meant by in that direction? In whichever may be the direction I am holding, okay, simple. If I am holding it here, okay, if I am holding it here like this, if I am holding it like this, then thermal stresses will be developed in this direction. If I am holding it like this, okay, if I am holding it like this, then thermal stresses will be developed in this direction. So where the restriction, okay, where the restriction is there, in that direction, thermal stresses also will be developed, okay. But if you see something, if there was a restriction, then deformation will be 0 in that direction, okay. Deformation is becoming 0 in the sense what? Strain is becoming 0 in that direction. But free expansion, free contraction case, thermal stresses won't be there, okay, sigma will be 0, but strain will be there because it is expanding or contracting freely. So I hope it is clear, right? Now let us talk about this strain which is developed first, okay. So let me take a member, okay, so with a length L, initially at a temperature Ti, okay. Now I am increasing the temperature to Tf, and let the change in temperature be delta T, okay, final minus initial. And due to increase in the temperature, this is getting expanded, okay, this is Li, this is Lf, okay. So there was a deflection or deformation which is Lf minus Li, okay. And it's pretty much straightforward things which we need to note here. What is that? Listen, let me take this is L itself, okay, let me keep this is Lf, okay, so Lf minus L, okay, the length of that initial member, that is L. One thing which you need to understand, increasing the body, okay, initially this body is at 20 degree, now I am increasing it to 30 degree, which means temperature difference was 10 degree. If I increase the temperature by 10 degrees Celsius, there will be some expansion. If I increase the temperature by 20 degrees Celsius, if I increase it by 30 degrees Celsius, what will happen to the expansion or what will happen to the deformation? The deformation is also going to increase. If the temperature difference is increased, then obviously the deformation of this body is also going to increase. So I can say that deformation, okay, or deflection is directly proportional to temperature difference. So if I am increasing more temperature, if I increase it by 20 degree, the deformation is going to be more compared to increase in 10 degree, okay. So delta is directly proportional to delta T, okay. Next, consider a member which is whose length is 10 centimeter, and consider another member whose length is 20 centimeter, and I am increasing this member by 10 degrees Celsius and I am increasing that member by 10 degrees Celsius. Which one is going to elongate more? A member of 20 centimeter, member of 10 centimeter, I am increasing the temperature by 10 degree. Initially both of them are at same temperature. I am increasing the temperature by 10 degree. I am increasing temperature of this body by 10 degrees Celsius. Which one will elongate more? Pretty much obvious. Length is going to get elongated by the one whose initial length is more, that is going to get elongated more, okay. Listen one thing, Why I am talking only about L? Because breath is also there, width is also there. If I increase the temperature, breath is also going to increase, width is also going to decrease. That is going to increase, that is going to change only. But I am not going to talk about that. Why unnecessarily have to include that? Because you already know. If I increase the temperature, breath is also going to increase, width is also going to increase only. Okay. So that is why I am not talking about that. Here L implies any linear dimension. It can be length, it can be breadth, it can be width, whatever it is. So the member which is having larger length is going to deform more, which means I can clearly say that this deformation is directly proportional to length. So by combining this, deformation is proportional to delta t into L, okay, delta t into L. And for removing this proportionality, sign, I'm adding a proportionality constant alpha. So alpha delta t L. So that is deflection delta. Okay, and this alpha is coefficient of thermal expansion. Okay, it is coefficient of thermal expansion or thermal expansion coefficient. This formula is important, you need to remember. Okay, if you want, you can keep this as delta L also, change in length. Okay, so delta L, change in length, instead of keeping it as delta L, change in length or deformation, that is equal to alpha delta t into L. Okay, listen now. This coefficient of thermal expansion is there, right? It is a property of the material. It is a material property. For example, if I use steel, okay, it will be having different thermal expansion coefficient. If I use aluminium, it will be having different thermal expansion coefficient. If I use copper, it will be having different thermal expansion coefficient. So, and based on that thermal expansion coefficient, what actually this thermal expansion coefficient is going to say as? Very simple. If alpha value increases, for example, just for an example, for any material, alpha is more. For one material, alpha is more. For another material, alpha is less. So the material which is having more alpha, the material which is having larger thermal expansion coefficient is going to expand more. Why? Delta L is directly equal to alpha delta TL. So if this is large, then delta L is also going to be more, right? So what are the things you need to note here? This is a material property and it will vary material to material. If I take steel, if I take aluminium, I will be having different thermal expansion coefficient. And what is the unit? See, it's very, very simple. Delta L is equal to alpha delta TL. So alpha is equal to delta L by delta T into L. And what is delta L's unit? Meter. Delta T unit, degree Celsius. Length unit is meter. So it is 1 by degree Celsius. 1 by degree Celsius. See, temperature difference you can take either in degree Celsius or in Kelvin. Okay, so that is not going to be like what I can say. That's not going to affect us because I'm finding temperature difference, right? So TF minus TI, which means obviously in Celsius or in Kelvin it's going to be same only. We are going to get the same answer. But most of the times for SOM we will be using directly. I will be using delta T as degree Celsius. Okay. But once we enter into thermodynamics, we will be talking more about this. Okay, that time you will have more clarity about this. Okay, about this degree Celsius and Kelvin. For mechanical students, not for civil students, right? So coefficient of thermal expansion, it's a material property, 1 by degree its unit is 1 by degree Celsius, and I said almost everything. Next, what we need to note? We need to note something, that is, we need to remember some constant value of this thermal expansion coefficient. By remembering constant value of thermal expansion coefficient, it will be very useful for us when we are solving some numericals. Right? These are some constant values which you need to remember. Okay. So for steel and concrete, the thermal expansion coefficient value will be in between 10 to 12 into 10 power minus 6. For brass, it is 19 into 10 power minus 6. Aluminium 23 into 10 power minus 6. Copper, it is 16 into 10 power minus 6. Even if you are not able to remember the exact values also, you need to remember this range, which one is greater than that of which one. So magnesium is greater than aluminum, is greater than copper, is greater than steel. If you're able to remember this, that will also be very helpful. Even if you're not able to remember the exact value, you just need to comparatively remember which one is greater, which one is having less. Okay, this is alpha value. Right. Now, this thermal stresses, if you ask me where these thermal stresses are present, or you can say practically where I can see. Simple, listen. See, you could have seen this actually. Yeah. So now you could see this, right? What is this? It is something which I able to represent. This is nothing but a railway track. Okay, representation of a railway track. I just try to represent you the railway track, and in general there will be some gap. If you remember, there will be some gap between a railway track. If there is a railway track, if it is a horizontal railway track, in between one railway track to other railway track, there will be some small gap. Okay, there will be some small gap between railway tracks. Why the gap is kept? Because during as the temperature changes, because as weather condition changes, temperature is going to get changed. If temperature is going to get changed, there is going to be expansion and contraction of this particular railway track. So if temperature increases and if it gets expanded, if there was no gap, then this member is going to offer a compressive stress. And due to that compressive, it is going to offer a reaction which is try to compress it, and due to that there will be development of compressive stress. Okay, so compressive thermal stresses. So to avoid that compressive thermal stress, we need to keep a small gap between railway tracks. Okay, and some of the key points regarding thermal stresses is, one thing I already said. What is that? If there was a restriction, in that restriction, in the direction of restriction, there will be thermal stresses developed. The next point is the thermal strains. Okay, so if it is freely expanding, if I increase the temperature, it's going to expand freely. Those thermal strains are what I can say, those thermal strains are reversible in nature. What is meant by reversible? If I'm heating it, okay, heating it from 20 to 30, it's going to expand. Once if I cool it, it's going to come back to the same value, right? If I'm going to cool it from 30 to 20 again, it's going to reach the same value. So that's what I'm saying, it is reversible in nature. It will expand. If I cool it again, it will come back to same place. So thermal strains are generally reversible in nature.